Every day, a mind-boggling volume of data is transmitted across the internet. To put an exact figure to it would be meaningless, since the figure would grow a little each day. With all that data being transmitted, it's understandable that transmission errors occur. This is when data arrives at its destination in a way that does not quite match its state when it began its journey. Some ones are zeros, some zeros are ones, and some bits are missing. This chapter examines how such errors are identified and resolved.
The simplest method is called a parity check. When data is transmitted in the form of a string of binary digits, an extra digit is added to make data always contain an even number of ones, or always contain an odd number of ones. Let's look at even parity. Suppose we want to send this data. In order to achieve even parity, we would need to add a 1 onto the end, since there are only 3 in our data.
The recipient computer, which knows that even parity is being used, checks for an even number of ones and disregards the last bit. Alternatively, if this was our original data, we would add a 0 to the end, since we already have an even number of ones. Odd parity works in the same way, but with an odd number of ones instead of an even number.
Parity checks are straightforward, but they have a significant flaw. Let's say we're transmitting this data, with the last bit included for even parity. If 2 digits were to be altered during transmission, the data still has even parity. So a parity check only works if an odd number of bits change.
Another approach is to use check digits. An ISBN, or International Standard Book Number, is used to uniquely identify books. ISBNs consist of 13 digits. A calculation is performed on the first 12 digits to produce the 13th, which is then included as part of the number. When an ISBN is entered or transmitted, that same calculation is performed on the first 12 digits. If the result of the calculation does not match the 13th digit, an error has occurred. Of course, this system is not perfect, as there is a 1 in 10 chance that a check digit can be accidentally correct for an invalid number.
Checksum is another approach, or rather a collection of approaches, as there are several ways to implement checksum. In its most basic form, it is a number that is sent along with transmitted data that contains a count of the number of bits in the data. If the recipient computer counts the bits and reaches a different number, the data sent does not match the data received. More sophisticated checksum approaches exist to ensure that the ones and zeros are in the right places as well as of the same quantity, but the principle is the same.
If a system is using automatic repeat requests, the recipient sends an acknowledgement to the sender after receiving each piece of data. If the sender does not receive this acknowledgement, it assumes the data was lost and sends it again. This continues until either an acknowledgement is received or the maximum number of attempts have been made. Oddly enough, automatic repeat requests is abbreviated to ARC.